Hello everybody, welcome to this lesson whereby we're going to talk about complex locus. So locus, these are just points that satisfy a given condition, and I want to demonstrate that using an example. Determine the locus defined by the modulus of z equals to 4. So z is just a complex number. So instead of writing it like this, we'll write it in its rectangular form. Okay, so we'll let the real part be x and the imaginary part be yj. We let z equal to that. Okay, the rectangular form of a complex number. So what we now have, okay, so what we now have is x plus yj. The modulus of that is equal to 4. And you know what these two parallel lines stand for? They stand for modulus. And from our previous knowledge, we know that getting the modulus of a complex number, all you need to do is you square root the square of the real part and the square of the coefficient of j. Okay, that should give you this. So get rid of this square root sign by squaring both sides. We remain with x squared plus y squared is equal to 4 squared. Okay, and notice now, take a good look at this equation. Yes, this is the equation of a circle. This is the equation of a circle whereby the center is 0, 0. Center is the origin and the radius is 4. Okay, so the locus of this, of modulus of z is equal to 4 is a circle with the center at the origin. This is a circle with a radius of 4 and the center at the origin. It will be something like this. Okay, so now is the locus of z equal to 4, which is x squared plus y squared is equals to 4 squared. Center origin and 4 units, and the radius is 4. Okay, let's try another one. Okay, let's try another one. Determine the locus defined by the argument of z is equal to pi over 4. So as usual, we replace z with the rectangular form. We replace z with the rectangular form of a complex number, and that is equal to pi over 4. Okay, now to get the argument of a complex number, we all know that it is the tan inverse of y, the imaginary part, over x, and that should give you 4. From our previous knowledge, we know that to get the argument of a complex number, you need the tan inverse of the coefficient of the imaginary part over the real part. So get rid of this tan by introducing it on the right hand side. So this will be tan pi over 4. Okay, we get rid of this tan inverse by introducing tan on the right hand side. Okay, so tan of pi over 4 is 1. Tan of pi over 4 is 1, meaning that the modulus defined, the locus defined by the argument of z is equals to pi over 4 is a straight line passing through the origin. Y is equals to n, y is equals to x. Okay, so it's a straight line. That's the modulus defined by the argument of z. So let's carry on. Determine the locus defined by the argument of z minus 1 is equal to pi over 6. So just the usual way, replace z with the rectangular form of a complex number. Argument z will be now x plus y j minus 1. Add the 1 there. That is equal to pi over 6. Okay, so this can simplify to the argument of, put the real parts together, x minus 1 plus yj is equal to pi over 6. Now let's get the argument of this complex number. Now to get the argument of that, as usual, it is the tan inverse of the coefficient of the imaginary part over the real part. Okay, and that should be equal to pi over 6. Get rid of this tan inverse by introducing tan on the right hand side. So you will get y over x minus 1 is equal to tan of pi over 6. You get rid of this tan inverse on the left hand side by introducing tan on the right hand side. Okay, so pi over 6 is 30 degrees. So you just do tan of 30. Tan of 30 is tan of 30 tan of 30 is 0.58. Tan of pi over 6. Pi over 6 is in radians mode. You can change it into degrees or work in radians, whichever you choose. It is 0.58. So this means that the locus defined by argument of z minus 1 is equal to pi x is 0.58 x minus 1. It's a straight line. Okay, a straight line with a gradient of 0.58. So that is that. That is how you tackle questions involving locus of complex numbers. Okay, thank you for watching. This is Understanding Math.